Okay, so today I'll continue talking about the strongly interacting matter. This time I'll go delve a bit more into the formalism that we use, discussing the equation of state of isospin asymmetric matter. So this is the outline. I'll follow a brief motivation, formalism, and some results. So to recap some key concepts of the last lecture, we have the density phase diagram, the temperature and baryon density plane. So for low energies, the quarks are confined in hadrons. If you increase this energy, they are deconfined to form the soup of quarks and gluons. Uh, some interesting objects that you can study are, for example, neutron stars. And you will notice that those stars they don't lie exactly on the temperature UV plane. They lie on this other axis here, which has a difference in the number of neutrons and protons. This is called the isospin density. And of course, neutron stars have more neutrons than protons, so they lie on this plane. They're very low temperature objects. And they lie on this isospin finite baryon density plane. So this is the axis that we want to study, the effects of this imbalance between neutrons and protons, or in terms of the quark content, an imbalance between down and up quarks. So to see this, define isospin a bit better. Finite isospin density is an imbalance between neutrons and protons in the system. We can define this as analogous to angular momentum. So the third component has a plus sign, 1/2 for up quarks, a minus sign, 1/2 for down quarks. So to calculate, neutrons are 2 down quarks and 1 up quark, so they have isospin minus 1/2, and protons have isospin plus 1. There are 2 up quarks and 1 down quark. And of course, system where this finite isospin is relevant are neutron stars, and maybe some heavy ion collisions as well, especially non-central collisions, have finite isospin effects. And another motivation for us to work with effective models is that LQCD simulations don't suffer from the sign problem. It's finite isospin density but 0 baryon density. So we can test our models and compare with these predictions. And another interesting thing of now a theoretical perspective, that pions also carry isospin. So a pion can have the neutron pion, which is a pair of an up quark or anti-up and an anti-up quark, or a down quark, anti-down quark for the neutral pion. For the charged pions, we have the up quark and the anti-down quark, and also the down quark and anti-up quark. And these charged pions, they carry isospin number, plus or minus 1. And remember, they're bosons, and if you have a chemical potential of this particle higher than the mass, you can have boson condensation. So this can have very interesting effects in the equation of states. So here we have, just to motivate, have a graph of some particle populations as functions of increasing baryon density. Using a manner that is better equilibrated and charged neutral. So what you encounter in the core of a neutral star, for example. So you can see that the higher number densities refer to the down quarks. There's a difference between the densities of down quarks and up quarks. We also have some density of electrons in the system, and for higher densities, the strange quarks starts to populate. So here you can see that you have finite isospin in a neutral star here. And you can also study the T and μi phase diagram, the isospin chemical potential. So for low energies, you have the same picture. Quarks confining hadrons, baryons, and mesons. as you increase the density, you can have formation of pion, charged pions. They form a Bose-Einstein condensate. Of course, if you increase the temperature, it is deconfined, and here you can have some kind of superconducting phase where they form super pairs. But we are interested in the zero temperature regime and finite UI regime to start. So I'll try to give a brief description of how you can obtain results in the Nambu Jona-Lasinio models, generally studying verify the effects of chiral symmetry, restoration, to have parts, 0 degrees of freedom, spinors, some 4-point interaction, scalar interaction, pseudo-scalar interaction, kind of 5 matrix, the interaction is stuff in G, and these Town matrices are the generators of the SU2 group. So, but we want to study finite isospin, and then the adequate basis would be the modification of these polymeristic bases by this expression. And here you can separate clearly the charged pion contributions, both tau plus and tau minus, and the neutral pion contribution, which goes with the tau 3 matrix. And of course, you still have the scalar condensate. Well, not condensate, the scalar fields, scalar interaction. So we work in a new mean field approximation. So what we do is we replace an interaction of two fields by an average and fluctuations. And we do the same for the pseudo-scalar interaction, average and the fluctuations. We can define some notation, the sigma, this is the pi plus and minus condensates. This is the neutral pion condensate, which is 0 in this case. And then we can iterate this formula, isolate the fluctuation here, two fields minus the average, or minus sigma. So we can take the square, goes like this, and we substitute the fluctuation, this term, and you neglect quadratic fluctuations. It goes away and you end up with this term. So what you did, you had 4 fields interacting in a point. Now you have an interaction of 2 fields in the presence of this average or this condensate. So in this prescription, the Lagrangian density can be written in this form, but we are not done yet because we need to include the isospin density. So isospin is a symmetry of the model. When you break the symmetry, there is a observed isospin number, crater, which goes with 1/2 in this term, observed current. And so you can include this coupled to the isospin chemical potential to your Lagrangian. And this term is, of course, breaks the isospin symmetry. And if you have a non-zero value of these condensates, pi minus and pi plus condensates, then you further break the symmetry and you have a Bose-Einstein condensate of charged pions. So, all these considerations, they will differ by a phase. Pi plus and pi minus, you can adopt this phase to be 0. And then the Lagrangian density can be written in this form. Everything that is between the anti-spinor and the spinor here is a propagator, which is the main object in this compute. This is just a potential term with 2 average fields. Once you have your effective Lagrangian, this is the inverse propagator. So use your thermodynamic quantities and use the partition function. It goes with the functional integral over these psi fields of the Lagrangian. If you compute this integral, you have the determinant of the log. Sorry. Then you compute the thermodynamic potential. You have the log of this partition function. do that, you have the log of the determinant of this object. Actually, the inverse of the object in propagator. So there's a lot of steps there that we have to skip, and you end up with something like this. These terms and an integral which depends on energies that go with the chemical potential and the pion condensate. They also depend on the quantities. The key thing here is that these energies depend on the isospin chemical potential. To find the sigma and minimize the potential, and solve the gap equations. These are the physical values of these compensates. And of course, from the thermodynamic potential, you can define all other quantities of interest, such as the pressure, the isospin density, the energy density, and the speed of sound. So I'll go through some works that we have done with this regime. So I mentioned that the Jona model doesn't start at peak speed of sound. This behavior is found by lattice simulations. The usual result of the NJL model is monotonic curve here, always increasing. But we know that the coupling of the model should be sensitive to the energy scale, and we wanted to see if a mu I dependence on this coupling to account for this behavior. So the answer was actually yes. So if you have this behavior as a spin coupling, you can reproduce the lattice data. And this behavior can be traced to the isospin density, which has these changes of curvature here, and these changes of curvature are reproduced in the coupling gene. Another thing we can study is the mesomixing and Bose-Einstein condensation. So if you have a Bose-Einstein condensate, you have one massive mode and one Goldstone mode. This has zero mass. So you can see here that after mu I is equal to the pion mass, you have a mode that goes with zero mass, with a positive pion. Another mode that is massive, and negative pion. The neutral pion doesn't feel these effects, it grows linearly here. There's a mix between the sigma and the two charged pions, whose masses depend on each other. Especially here. And another thing we can study is that if you study finite temperature field theory, you see that all temperature dependent terms or medium dependent terms are finite. But we had a potential like this, and these integrals divergent. What we did was simply take a cutoff here. It's a parameter of your model to fit. But doing this, you are cutting medium contributions. Remember that these terms, these energies, have a chemical potential inside. And this is called the traditional regularization scheme. And we can ask ourselves if there's a way of separating these contributions such that you can integrate only vacuum quantities and not quantities that depend on gas, rather regulate only the vacuum. This is called the medium separation scheme. You have to do a series of subtractions. You will end up with some expression that looks like this. I will not go over all the terms. The idea is that you have an integral that is divergent, another integral that is divergent. These terms all finite. You can integrate up to infinity. And these two divergent integrals that remain are only dependent on vacuum quantities. This is the vacuum coordinates. That's density 0. Same for this integral. So only these two are regulated. These terms totally finite. And you can see that the speed of sound is the linear results we have. The work is in development. We have 3 lattice density data sets for the speed of sound. And with the traditional regularization scheme, speed of sound grows. See this kind of peak here, but then it keeps growing and eventually diverges. That's because the gap or the pion condensate goes to 0 at high density. but this doesn't happen in the medium separation scheme. You actually have the correct behavior. Speed of sound presents the speed, goes 1/3, the ionizing density grows. So that's what we have done so far. Just end here, so for your attention.